Hi, everyone. My name is Ellen Foley, and I am a master's student in Dr. Alan Steinman's lab at the Annis Water Resources Institute out of Grand Valley State University. Today, I will be presenting some of the preliminary findings from my thesis research looking at the impacts of excess chloride on phosphorus in an urban eutrophic lake. Anthropogenic inputs into freshwater environments are notably degrading these ecosystems. Eutrophication resulting from excess nutrients, namely phosphorus, and salinization resulting from excess salt are two prominent threats to freshwater systems and are known to cause a suite of ecological problems. Excess salt may arise from a variety of sources, though one of the more common culprits, especially in northern temperate regions, is road salt. The amount of road salt applied annually in the United States has increased by 23 million metric tons over the last half century, with large amounts running off into surrounding waterways. In lakes, high amounts of road salt can alter the hydrology by creating a dense saline layer at the bottom that prevents seasonal turnover, leading to low oxygen conditions. Additionally, excess salt can negatively impact freshwater organisms from all trophic levels. The EPA has a chronic toxicity threshold for fluoride set at 230 milligrams per liter, though studies have observed negative effects on biota even below this threshold. Higher salt concentrations may also alter lake water chemistry by enhancing cation exchange and increasing the mobility of other contaminants in the water column. Excess phosphorus runoff into freshwater systems can cause algal blooms that lead to low dissolved oxygen, unsightly aesthetics, and even fish kills. Additionally, toxins may be released into the water should a harmful algal bloom form. Internal loading of phosphorus may perpetuate the effects of eutrophication by releasing phosphorus into the overlying water column from the benthic sediment. One understudied concern is that excess salt can induce or even exacerbate eutrophication through an increase of phosphorus to the water column via internal phosphorus loading. This phenomenon may occur when that dense saline layer of water forms at the bottom of the lake, preventing the lake from mixing and creating anoxic conditions in the hypolimnion. Under anoxic conditions, iron is reduced and releases the sediment-bound phosphorus into the water column, where it is now available for uptake by biological organisms such as algae. This process of salinated-induced internal phosphorus loading is essentially a ticking biological time bomb. If the high concentrations of phosphorus building up at the bottom of the lake were eventually mixed with the upper layers of water where light is available, a severe harmful algal bloom could form. This is discussed in the literature, but there is currently little to no empirical evidence demonstrating this theory. This is concerning since salinization and eutrophication may often be co-occurring problems, yet they're rarely studied concurrently. Therefore, we have a limited understanding of their combined impacts on lake ecosystems. My research aims to address some of this knowledge gap by investigating the impacts of road salt on phosphorus in an urban lake. I had two primary research questions, and first wanted to know how higher road salt concentrations impacted lake water quality, and second, if excess salt influences internal phosphorus loading rates. Unfortunately, there's a lake in Grand Rapids, Michigan that is a perfect mesocosm for studying the impacts of road salt on phosphorus dynamics. Church Lake is located on the east side of Grand Rapids in the lower peninsula of Michigan. The surface area of the lake is around 7.5 hectares with a maximum depth of just over 16 meters. Our lab at AWRI has been taking monthly water quality measurements in situ and taking water samples for analysis at the deepest part of the lake since August of 2020. And in April of 2021, we added a second site for water quality measurements on the east side of the lake where a small tributary enters, which you can see here in the blue arrow. This tributary is largely fed by stormwater runoff from the East Beltline, which is a Michigan state highway. And the East Beltline is pretty heavily salted during the wintertime and is believed to be the source of most of this salt entering Church Lake. We've been measuring the tributary on a bi-monthly basis and have been also collecting additional storm samples and snowmelt events to capture that flush of chloride entering into the lake. Here are some of the results from this tributary and lake water quality observational study. Here we see the concentrations of chloride measured in the tributary from August 2020 through March 2022 in yellow. The dark dashed line signifies the US EPA chloride chronic toxicity threshold for freshwater biota at 230 milligrams per liter. A majority of the samples taken in the tributary have been above this threshold, even during months like the summer, that don't have a lot of road salt application. The highest peak was measured during a large snowmelt event in February of 2021, and chloride levels nearly reached 1,000 milligrams per liter, which almost qualifies as brackish water. On the right, you see a relationship between the chloride and specific conductivity. The conductivity, which is measured in blue on the left, is measured in situ with a YSI SAN and accounts for the amount of dissolved ions in the water. The strong linear relationship between chloride and conductivity suggests that chloride is the dominant ion in the tributary water. And therefore, we can use conductivity as a proxy for chloride since this is measured in situ in the field and can give us a good picture of the amount of salt that there is before we take it back for analysis in the laboratory. And here are some of the results from our lake water quality survey. Here we see depth time isoplots of chloride on the left and total phosphorus concentrations on the right. The hypolimnion of the lake has high chloride concentrations consistently above 200 milligrams per liter at or below 10 meters of depth. And around that same depth, we see extremely high concentrations of phosphorus. And just to show you how high these phosphorus concentrations are, Lake Michigan typically has phosphorus concentrations around 1 to 2 micrograms per liter, and lakes are usually considered eutrophic around 20 to 30 micrograms per liter of phosphorus. The phosphorus concentrations that we're seeing at the bottom of Church Lake have exceeded 7,000 micrograms per liter. So even if a small portion of that phosphorus were to reach the surface where there is enough light for photosynthesis to occur, there could be devastating algal blooms on this lake. Additionally, the disparity between the surface phosphorus, which is averaging around 20 micrograms per liter, and the bottom water phosphorus concentrations suggest that internal phosphorus loading is the primary mechanism for the increased phosphorus that we're seeing in the water column. The relative stability of the concentrations, meaning that they're stable at 10 meters depth, also suggests that the lake is likely not fully turned over during our study period due to that dense saline water at the lake bottom. To address the second research question and further investigate the impacts of higher chloride on internal phosphorus loading, we conducted a sediment incubation study to look at how chloride impacts sediment phosphorus release. We collected 16 sediment cores near the 2 sampling sites in Church Lake and incubated them for 25 days under exposure to 1 of 4 of the following treatments: anoxic and low chloride, oxic and low chloride, anoxic and high chloride, and oxic and high chloride. The anoxic cores were bubbled with nitrogen with a CO2 buffer for the CO2 to buffer pH, and high chloride cores had an average concentration of around 300 milligrams per liter of chloride, which is similar to concentrations that we found in the hypolimnion of Church Lake. Throughout the 25 days, we took water samples from the overlying water column for TP or total phosphorus, SRP for soluble reactive phosphorus, and chloride. At the end of the experiment, the top layer of the sediment was analyzed for different phosphorus fractions to determine how much soluble reactive phosphorus is mobile or stable. Mobile phosphorus is what is available for uptake by biological organisms and can be seen highlighted in the blue, and stable fractions are highlighted in black. The fractionation scheme is demonstrated on the right side here, and the rest of the sediment was then measured for the metal content of metals that typically bind to phosphorus in the sediment. Here are some of the results from this sediment incubation experiment. These graphs show the sediment phosphorus released from cores at both sites over the 25-day incubation period. The left graphs represent total phosphorus, and the right graphs show the soluble reactive phosphorus. Note the different scales for the SRP and TP. We saw high release followed by initial decline, likely due to disturbance in the settling of sediment during the first few days of incubation. Anoxic and anoxic plus chloride cores appeared to have the highest phosphorus concentrations in the water column throughout the duration of the study. These graphs show the average maximum apparent P release with standard deviation in the treatments from each site. Typically, flux or phosphorus release is calculated using the concentrations of TP or SRP at time t, subtracted by the initial concentration of TP or SRP. However, Maximum release is based on the phosphorus accumulation in the water column over the time period that resulted in the maximum apparent release rate, the caveat that the initial and final samplings cannot be consecutive dates to avoid potential short-term bias. That difference is then divided by the number of days and multiplied by the volume over the surface area of the core to get the release rate. Mean apparent maximum TP release was highest for the anoxic and chloride treatments for both sites, averaging around 1.45 to 2 milligrams per meter squared per day of phosphorus. However, this was not necessarily the case for SRP, as this treatment was only highest for Site 1. Site 2 had highest SRP release rates for just the anoxic cores. Lakes are quite heterogeneous, and differences in sediment composition may have contributed to variable outcomes. However, these results still show that higher salt concentrations may increase phosphorus mobilization out of the sediment and further increase internal phosphorus loading rates. Once again, fractionation is that process that differentiates mobile and stable phosphorus fractions. The highest amounts of SRP in the sediments were found in the stable HCl and NaOH fractions. Site 1 had higher amounts of phosphorus in the mobile buffer dithionite or BD fraction, suggesting that more phosphorus could have been mobilized and explaining the higher SRP release rates that we saw from Site 1 in the previous slides. All in all, this study has implications for the remediation and management of urban lakes or lakes experiencing increased concentrations of chloride and phosphorus. We have seen that higher concentrations of chloride from road salt can promote internal phosphorus loading in lakes from anoxic conditions formed through the reduced lake turnover, potentially leading to eutrophication and algal blooms. Additionally, higher amounts of chloride may directly increase sediment phosphorus release, further contributing nutrients to the water column. This may be due to mechanisms of anion exchange or through the reduced stability of humic iron aluminum phosphate complexes due to increases in ionic strength and decreased pH from higher salt concentrations. Sediment phosphorus dynamics responding to salinization are complex and warrant further exploration, especially in the context of redox changes. This is important for helping us understand how lakes are influenced by excess nutrients and salt, so that we can make scientifically sound lake management decisions and promote the successful remediation of lakes experiencing these issues. For example, based upon the results from our study, we propose a restoration strategy for Church Lake that involves the removal of excess phosphorus from the hypolonion before addressing the high chloride concentrations, as a premature breakdown of the salinity gradient could allow large amounts of phosphorus to reach the surface, stimulating algal blooms. In the end, while road salt increases driving safety in the winter, current road salt application practices impairs water quality. Fresh water is one of our most precious resources, and we need to find ways to reduce the amount of road salt ending up in our aquatic environments and search for better alternatives to ensure that our fresh waters stay fresh. And with that, I would just like to acknowledge following organizations for providing funding to my project. I'd also like to thank my advisor, Dr. Al Steinman, my thesis committee, and lab members in the Steinman Lab and at AWRI for all of their help and insight into my project. And finally, I'm very appreciative of the Church Lake Housing Association, specifically the Gardner and Van Tol families, for granting me access to their properties and graciously allowing me to use their personal watercrafts. Thank you all for listening. This concludes my presentation.